Alright, so the first part of chapter 8.3 was calculating a confidence interval for a population proportion. Now, the second part of chapter 8.3 is finding the sample size needed to estimate the population proportion, basically given a desired margin of error. So this is basically the same thing we did before. Now, of course, the confidence interval for a population proportion was the point estimate plus or minus this z-critical value multiplied by the standard deviation of the proportion. And recall, that is the margin of error. So basically, your margin of error then is equal to that quantity right there. And once again, we're going to be given a desired margin of error, a z-value based on a confidence level, and then hopefully we're going to know a sample proportion, and we want to find the sample size necessary. So what I've done in this next step is all I did was I took this expression and I rearranged it algebraically to solve for n, and we have that expression right there, where the sample size required is just equal to the z-value squared multiplied by the sample proportion multiplied by 1 minus the sample proportion divided by that desired margin of error squared. One thing I do want to mention though is sometimes if you're figuring out the sample size needed, you don't even have any idea what the sample proportion might be. In situations where you don't know what the sample proportion is, you just use 0.5 just basically as your best guess. Alright, let's check out an example where we want to calculate the sample size necessary to estimate a population proportion with a certain margin of error. So we're going to check out 8.3.57 from your MyMathLab or your MyStatLab homework, which is number 12 from your 11th homework assignment. So the problem reads, a survey of 452 women revealed that 48% wear flat shoes to work. There's two parts to it. Part A asks us, use the sample information to develop a 99% confidence interval for the population proportion of women who wear flat shoes to work. Alright, so first off, of course, here's our formula for the confidence interval for a population proportion. P hat, or our sample proportion, is just going to be 0.48 because 48% of the females wear the flat shoes to work. So we plug that in, 0.48, then plus or minus. Now, our z-value is going to be based on the 99% confidence interval. You look that up on the standard normal distribution, and you should get a z-value of 2.57, 2.58, or right between those two, and 2.575. If you use any of those z-values on the exam or on the homework, you should get the right answer. Definitely on the exam, you get the right answer. So 2.575, then multiplied by all that square root of the sample proportion, again, which is 0.48, multiplied by 1 minus the sample proportion, divided by our sample size, and our sample size was 452. So of course, I'm just going to take the 0.48, subtract that quantity, and then add it to find the lower and the upper bounds. And I came up with 0.419 to 0.541. Now, part B is actually what I really wanted to talk about, which is, well, let me read the problem statement. Suppose that people who administered this survey now wish to estimate the population proportion of women who wear athletic shoes to work with a margin of error of 0.01 with 95% confidence. Determine the sample size required. So once again, here we have the formula for the sample size required, basically when we're given a margin of error based on a certain confidence interval and then a sample proportion right here. And that should be another p hat right there. So of course, let's just plug in our values. Our z value based on a 95% confidence level, again, is going to be 1.96. And that is squared from the formula. and then multiplied by our sample proportion, which is again 0.48, multiplied by 1 minus the sample proportion, or 1 minus 0.48, and then that's all divided by the desired margin of error squared, in this case 0.01 squared. You do all that and you calculate out n, and you should get 9,588.6. Once again, though with sample size, you always want to round up to the nearest whole number. So your actual n is just that rounded up to the next whole number, or 9,589. And there we got it.